Okay, this video is for CEP 636 and we're talking about the renal system. I'm a bit under the weather, so hopefully I won't sneeze too much, but the truth is I'm not starting the recording from start just because of a bit of a sneeze, so I apologize. And of course, my voice is always weird, but it's probably going to be a bit more weird than it usually is. I might jump over several slides. I've went over the slides, and some of them are very simple to understand, and some I'll highlight certain points that I think are important. And please, I'm begging you, if you go over the book and then the presentation and then the video and or videos and still have questions, do not hesitate to contact me. I'm begging you, don't keep it inside. That's not how it's supposed to work. With that said, let's start. So we have 3 slides that are just titles. So I'm going to slide 4. Of course, just to make sure, TBW is total body water, meaning the amount of water in the body. And then we look at the idea of ions. When you hear the word ions, I want you immediately, as clinical exercise physiologists, to think about electrical conductance or neural conductance. If you have an imbalance of ions, you have a serious problem at the level of the cell. We'll learn about this in pathophysiology as well. But immediately, if I say ions, you say neural conductance or electrical conductance. Very, very important, not only for the exam. Then in regards to slide 5, I just wrote one remark. You see how many processes, huge central cardinal processes the renal system is in charge of. So my remark was, do not mess with the renal system. The renal system is a major system that we all tend to forget about in a way as clinicians, and not focus enough on that system. So I want you to understand that any problems in the renal system is going to cause problems in the nervous system and the cardiorespiratory system. So very, very important system. Regulates blood pressure, regulates hydration of the body, regulates hormonal balance, and many, many, many effects, as we will see. It's pretty simple to understand on the one hand, but very important as well. So on slide 7, Ne is norepinephrine, a very potent catecholamine, very potent effector, especially during exercise. And then when we're talking about RBF, we're talking about renal blood flow, and when we're talking about GFR, we're talking about glomerular filtration rate. Basically, renal blood flow, the volume of blood that reaches the renal system, especially the kidneys, and then GFR, how much of that blood is filtrated. And when we're talking about rate, we're talking about obviously some kind of volume per minute, per second, etc. The system is tightly regulated by very potent hormones, and the system affects hormones. So there's a lot of feedback loops, a lot of them, that regard to the renal system. Then one of the major rules to understand the renal function, I'm going to say this again, one of the cardinal, major, central, important things to understand about the renal system is that water follows sodium. So does chloride. Wherever sodium goes, water goes with it. So it is a prime way or influencer of the amount of water that you have or lack. I'm going to say this again. Sodium is a major influencer of how much fluids, especially water, you have in your body. That affects blood pressure. It affects hydration. It affects so many different aspects of function. Wherever sodium goes, water goes. If you are reabsorbing sodium, you are bringing in water back into the body, not losing it. If you lose sodium, if you excrete sodium, you're losing water with it. If you're moving sodium from the ICF to the ECF, you are moving water and chloride with it. Okay? Now, an FYI, when you sweat, your sweat is mainly made of water and NaCl. How surprising. Okay, what else? Blood pressure in slide number 8, sorry, in slide number 8. You have to understand blood pressure is a driving force, meaning that it is important to normal function. When blood pressure goes up, the force that drives blood forward goes up, meaning that you are applying more force to the environment, but also making blood, in this case a tissue, move forward faster. You are also affecting mechanical gradients because you're elevating the value in one part of the phenomenon, the process, relatively to the other, and the gradient is equal to the gap between the two, the difference between the two mathematically. So very, very important stuff here. Obviously, blood pressure is a major driving force of circulation and cardiorespiratory function. So now you can understand why people that have problems in their kidneys are very fast, if they're not treated, of course, going to have very quickly problems in their cardiorespiratory system and other systems as well. Slide 9, we can talk about loops of feedback. The loops are feedback dependent. Then in slide 11, basically just a list. We're not going to start to explain each one, what it is and what it means, just an FYI. I'm not going to emphasize that. I'll just make sure that you know that RSNA is what we call renal sympathetic nerve activity, meaning how much how active is the sympathetic nervous system in regards to the kidneys or the renal system. Slide 13, RPF. RPF is renal plasma flow, as distinct from blood flow. So there's blood flow and there's plasma flow. Then in slide 14, in the second bullet, we're talking about a decrease of 35.5%. That's more than 1/3. That's a lot. That's a lot to decrease. Then in the third bullet, once again, slide 14, we're talking about constriction. Constriction means that the vessel's diameter decreases, blood pressure goes up, blood flow goes up, but the overall volume goes down. So supply or delivery goes down. Then we can talk about cardiac output, CO, which is in liters per minute. This is obviously a cardiac value or aspect. Talking about slide 15. Wait a minute. I have a sneeze coming. Wait for it. Wait for it. Whew. Sorry about that. Okay, I'm back. So we see that at rest, RBF is 20% of cardiac output. That translates to 0.2 times 5 liters per minute, which is roughly 1 liter per minute. And then, not roughly, it's accurately. And then we can talk about at exercise, it goes down to 3%, which is 0.035 times 25 liters if you're non-trained, which equals 0.8075 liters per minute, or 875 milliliters per minute. Just in case you needed to calculate, there will be no calculating calculus questions in the exam, so you're good to go with mathematics. That's for Maggie. Just kidding, Magster. I had to. We see that we have lower peripheral resistance. Lower peripheral resistance always improves the function of a system. The less the organ, the system resists you, the easier it is to have something flow through the system in case of fluids. BV is blood volume, just to clarify. Then on slide 16, we're talking about a mechanical gradient, which is a driving force of the system. We can see that in this case it's one directional in the renal system when we look at bullet 3. Moving to slide 17, once again and again and again until you get it. Pressure is a term from mechanics in physics. It is a driving force of the system, and that is in the background of slide 17. ANP is a natriuretic peptide. It's actually, there's ANP, BNP, and CNP. These are very potent substances, natriuretic substances that are cardinal to function. And for instance, BNP, which is brain natriuretic peptide, is a cardiac biomarker of cell damage or cardiac damage, dysfunction. It's used to diagnose heart failure and cardiac issues. Then in slide 18, what did I write here? Oh, we're talking about the idea of prevention of needing to pee, and it allows blood pressure elevation. We're talking about the idea of how the permeability of the membranes decrease. So that's part of the mechanism that allows us not to pee during exercise and elevate blood pressure in order to better function according to the demands during exercise. Then in the third bullet of slide 18, we're talking about albumin. Albumin is the most common protein in plasma. It's about 50% of the total amount of proteins in plasma. It helps maintain what we call oncotic plasma pressure, which is very important to the function of circulation. And this protein is a major influencer. It's cardinal to maintaining blood volume and to transporting non-soluble substances in the blood. Then going to slide 20, just want to remind you that the sympathetic system deals with transitioning from rest to stress situations and maintaining function at a certain stressful situation, so anything that is not rest. And then the parasympathetic system takes you from that stressful situation back to rest and maintains responses and function during rest. In order to accommodate the need to react very fast and get the body into a defensive kind of situation, the sympathetic system is wired in such a way that it can activate multiple organs at once, whereas the parasympathetic one cannot. So that's part of what's written here in slide 20. So I wrote to myself, the sympathetic system operates all or activates all at once versus the parasympathetic system that activates one by one. So all at once versus one by one. I hope that's simple and clear. Then in regards to slide 21, we are talking about the idea that you cannot filtrate something that you did not receive. So if the kidney does not receive blood, how is it going to filtrate that? So that's the point, that's the explanation to the bullet on slide 21. Excuse me. Then if we go to slide 23, the question is how much of the plasma is actually filtered, right? So that leads us to the formula that FF, filtration fraction, equals GFR divided by RPF. I want you to remember that formula if you don't mind. So that's what's written in slide 23. In slide 24, regarding the third point, the third bullet, obviously loss of sodium would lead to water loss. So preventing that is great for the body. Then going on to slide 26, we can see that when we're talking about concentration, we can keep the concentration the same even if volume changes. And that's what we're trying to do. So basically we're talking here, especially in the fourth bullet of slide 26, we're talking about a balance, the balance in between intake and loss through urine. Going to slide 27, we're talking about sweat or sweating being the major avenue of sodium loss, whereas sodium retainment through the kidneys and urine is the major way of either reabsorption or prevention of loss to start with. In the third bullet on slide 27, if we're talking about less urine production, we're also immediately decreasing sodium loss, and by that, water loss. In regards to slide 28, MVO2 is maximal aerobic capacity. And we see that as MVO2 goes up, sodium excretion goes down. That allows us to operate at higher levels of aerobic capacity or physical capacity. So it makes sense. Continuing to slide 29, we see in the second bullet that we're talking about a neural influence and not a chemical influence, meaning that the change is coming due to CNS or central nervous system activity and not changes at the chemical level. Then the third bullet on slide 29 deals with the idea that you should not lose more than 25% of sodium, because without external help you will induce a deficit. So up to 25% the body is able to battle by itself and balance. Above 25%, it is not able to balance without external intake of sodium. Please remember that fact. Then in slide 30, we could talk about aldosterone. Aldosterone basically causes blood pressure to go up. It's in charge of maintenance of sodium and water. And then when we talk about angiotensin 2 or ANG2, it's a great vasoconstriction or constrictor, sorry, meaning it decreases the diameter of the vessels and helps elevate blood pressure. When ANG2 goes up, ADH goes up as well. Continuing to slide 32, just to play a bit with numbers. So the second bullet is talking about water loss, right? So I calculated the average person in physiology is regarded as someone that is 70 kilograms, which is the equivalent of 154 pounds. So we multiply that by 2.2, right, to get that in pounds. So at rest, if you weigh 70 kilograms, which is once again the average person in physiology, by 0.3 milliliters per kilogram per minute, then you're losing 1 1/4 of a liter of water per hour. Obviously, that's the importance of hydration. Then, if you are well trained and you are now at maximal exercise or capacity, you can lose 4.2 liters of water per hour, which is a lot. So that's in regards to slide 32. Then in regards to slide 33, notice in the second point that we have a ratio of 1:1 for every molecule or ion, and that's very important. It's easy to calculate, and it means that the same system can balance both water and ions and blood pressure, which is great. So that's where I'm going to stop this video, and I will continue from slide 36 in the next one. Stay tuned.